Hello dear students, today we will discuss Kepler's law of planetary motion. We are discussing our gravitation chapter. We have already discussed about the Newton's gravitational law. We know about Newton's gravitational law. Now today we have to discuss Kepler's law of planetary motion. Okay, you can see in this picture he is a Kepler. Okay, this his name is Kepler. He is a physicist, you can say scientist, who give three laws which describe the motion of planets around the sun. Okay, so there are three laws of Kepler's. You have to remember all these three laws. These laws are very important. Okay, first law, Kepler says that you can read from here also. The planet move in elliptical orbit around the sun, with the sun at one of the two foci of the elliptical orbit. Okay, what does it mean? Let me explain the things. You can see here, this is sun and this is planet. Okay, according to Kepler, always planet revolve around the sun, and the path of this planet is an elliptical, not circular. We suppose that it is circular, okay, but it is not circular. According to Kepler, it is elliptical. Elliptical means just like oval shape, not perfect circle. This is oval shape. Okay, like this. Okay, next thing, the sun situated at one of the foci of the elliptical orbit. Foci means this is a plural form of focus. There are two focus in elliptical shape. Suppose that one focus is here and one focus is here. Okay. So the concept is this, that Kepler states that all the planet revolve around the sun in an elliptical orbit, and the sun situated at one of the foci of the ellipse. You can see here this diagram explains, this diagram shows about Kepler's first law of motion. Okay, now move to second law of motion. You can see here Kepler's second law. The thing is, each planet revolve around the sun in such a way that the line joining the planet to the sun sweeps over equal area in equal interval of time. Okay, what does it mean? It means that you can understand it by this diagram. Suppose this is a planet. Okay, planet position, at first the planet position is a dash, and after time t this planet moves to b dash. Okay, let me revise this one, that suppose a planet is situated at a dash, and after time t it is at b dash. The same thing here for that planet also. Suppose that planet at any time is at a, okay, and after the same time small t it moves to b. Got it? Then the area from sun to that sun means this area. In first case, you can see here, in first case, when planet moves from a dash to b dash, the area crosses by the planet. Area crosses means we will join the line from a dash to sun and b dash to sun. So the area between this area, we can say area of a dash b dash c. Okay, we can write a dash b dash c. This area is equal to area of this part. This part. Okay, it means this is a second statement of Kepler. Each planet revolve around the sun in such a way that the line joining the planet to the sun sweeps over equal areas in equal interval of time. We supposed that in time t the planet moves from a dash to b dash, and in the same this time interval t this planet moves from A to B. So the area sweeps by that planet in this case should equal in this case. This is a second law. Okay, it means that when sun when planet closer to the sun, the speed of planet is faster. This point should remain in your mind, that when a planet is closer to the sun, it moves faster in compared to the when a planet is far from the sun. Okay, this is Kepler's second law of. Okay, now Kepler's third law, you can see here, the cube of the mean distance of a planet from the sun is directly proportional to the square of time it takes to move around the sun. What does it mean? That, as we know from first law, always planet revolve around the sun in a elliptical orbit. So the time period of that planet, time period means to complete one round, the time taken to complete one round, that is called a time period. So the time square of the time period of that planet we can write as like it t square. This is always directly proportional to the distance of the planet from the sun. This is a distance. Okay, suppose this distance is r, so r cube. This is a third statement of Kepler's. The cube of the mean distance of a planet from the sun is directly proportional to the square of time it takes to move around the sun, or you can say t square proportional to r cube. T for time period of a planet, r for the mean distance between the planet and the sun. So these are three important laws which has given by Kepler. You have to remember all these laws. Thank you, dear students.